Hello, my name is Rana, and I'm a PhD student at Tel Aviv University under the supervision of Danny Cohen-Orr and Raja Giras. Today I'll be presenting our work called Mesh CNN. CNNs work really great on images for tasks like classification and segmentation. The combination of convolution and pooling layers results in a robust learning framework. It's straightforward to apply convolutions and pooling on images since they are densely and uniformly sampled on a grid. However, extending these operators to irregular domains is not a trivial task. In 3D deep learning, we also want to classify and segment 3D shapes. Some approaches convert the shape to a regular representation and then use standard image CNNs. Other works convert the representation to point cloud and develop irregular CNN operators to work on this type of data. However, the mesh has many advantages compared to the point cloud. Meshes are an efficient, non-uniform representation which only need a few large polygons to represent flat, simple surfaces. They also explicitly represent the topology, or the surface. For example, the mesh, unlike the point cloud, can distinguish the left from the right camel joints, even though they're close in Euclidean space, through the distance on the mesh surface. So, meshes are a list of vertices, edges, and faces, which together define the 3D object. The problem is that every vertex has a different number of neighbors, and there is no order. Before I get into the details of our pooling operator, I want to highlight a few points first. We use pooling to reduce the number of features. By eliminating non-informative features, we're able to strengthen the learned representation. For example, say we train one network to classify whether vases have handles, and another to classify whether they have a neck. Since we allow the network to choose which shape attributes to focus on, the mesh poolings or simplifications will be different. Okay, so Mesh CNN is a convolutional neural network designed specifically for triangular meshes. Instead of operating on the vertices, we operate directly on the mesh edges. First, we extract several basic geometric features for the network input. Then, convolution is applied on edges and the 4 edges of their incident triangles. Then, pooling is applied via an edge collapse operation, which retains surface topology, generating new mesh connectivity for the subsequent convolutions. Notice that every edge in a manifold triangular mesh is incident to 2 faces, which makes our fixed size convolutional neighborhood of 4 edges. We use the face normal to define a consistent ordering for the convolution. So we learn convolutional filters, which are applied on each edge feature and the 4 neighboring edge feature vectors. We take the magnitude of each feature activation vector and delete edges with the smallest norm. So the 3 features in each triangle are merged into one new feature using average pooling. We also update the mesh connectivity, which gives us new edge neighbors in the next convolutions. The classic edge collapse preserves the original shape by removing edges with a minimal geometric distortion. But mesh pooling learns which edges to collapse. By deleting edges with the smallest feature activations, we learn which edges to collapse, which has 2 main advantages. The first is that we're able to strengthen the learned feature representation by eliminating redundant information. The second is that it enables us to visualize what the network has learned. This gives us some insights into generalization and gives us clues about robustness to real-world use cases. Okay, so I'm only showing a few results of MeshCNN on tasks of classification and segmentation. Please see our paper online. We achieved state-of-the-art results on 4 different benchmarks. So for classification, we have a convolution and pooling layers, which are followed by a global pooling layer before the fully connected layers. We also developed an unpooling layer, which we use for fully convolutional tasks, such as segmentation. Okay, so here's some more segmentation results. The network learns to predict a class label per edge, because we are working on the edges. So to wrap up, MeshCNN is a general method for using neural networks directly on triangular meshes. Our spatially adaptive pooling provides visual cues and insights into what the network has learned and also strengthens the learned feature representation. And please check out our paper online. I'll be around the conference today, or you can contact me and feel free to reach out after.